What we're going to start with is we're going to compare the heights of boys and girls aged 14. This is ones where boys will be bigger. We're going to start with samples of size 30. I'll just start it playing. Okay, up the top you'll see those are the population distributions for the boys of age 14 and the girls of age 14. And down the bottom we're slowly taking samples of boys and girls, I think 20 of each, and we're playing it fairly slowly to start, just till you start looking at the features. Watch the movement of the medians. Watch the boxes getting fatter and smaller. Watch the whiskers getting hugely different. Okay. What the length of the whiskers are reflecting is the range, right? And that's why the range is such a lousy measure of spread. It's so unstable. And we should be trying to stamp it out. So you can help us try to stamp it out. Okay, so that's just a setup one to get at the idea. Now we're going to compare the heights of 14-year-old girls with 14-year-old girls. Now, why am I doing that? Each time I'm sampling from the same population, so all the movement I see now is coming from the act of sampling. All the movement's coming by the random process of who I actually get in my sample. There's no real movements happening at all. And just start watching that. The samples of size 30, we're getting quite a bit of movement. We're getting a lot of variation in the widths of the boxes. And of course our whiskers do funny things. I've forgotten how many of these I do, but I'm going to then switch to a sample size of 10 soon. We're still on doing these 20s. Are they finished yet? Okay, now we're getting it with 10. This is going to be even more extreme. And one of the things we're going to advocate is you don't use samples as small as 10. There's a lot of variation, a lot of movement, and you'll see some of the boxes get quite weird looking. You have medians sitting on top of quartiles, all sorts of weird stuff goes on. Sometimes you get quite large visible separation. Huge variation in box widths. And all this is just the sampling, just who by chance we happen to get in our samples. Go to another extreme. We'll start taking 500 at a time this time. Again, you'll see the dot plots are still sitting in below. They've turned into little histograms, haven't they? There's much less variation. You'll notice the whiskers still sometimes jump quite a bit, just showing the instability of the ranges. But if anything, I think you might be surprised by how much variation there still is at 500. Not so much variation in the median, yeah. And if we were looking at averages instead of medians, there'd be even less variation. So there's 10 again. And there's 500 again. Okay. Now we're stepping up a level to curriculum level 7, which is year 12, sixth form. Now this is something which is basically a translation simplification of people who have come across notched box plots. something invented by Tukey back in the 70s, and a lot of statistical packages, you know, a highly respected sort of way of including uncertainty information. Well, this is just a quick and easy way of doing that. So what we're doing here is we're going to draw on our box a line that goes from the median up 1.5 interquartile ranges divided by the square root of sample size, and down 1.5 interquartile ranges divided by the square root of the sample size. So basically, what's the interquartile range? It's the box width. So it's 1.5 box widths over square root sample size. Now what that gives you is actually an informal confidence interval for where the real median is. It catches the real thing about 90% of the time. So you can appeal to that. You know, you've drawn this on here, or better still, software's drawn this on here, and we'll make sure the Census at School site software does draw these things on for you so that people aren't sort of bogging down in this all the time. But what you can appeal to is, I think the real A median is in here somewhere. I think the real B median is in here somewhere. They're separated, no points of contact, so I think these things are different, so B's bigger. It's very intuitive once you've got the little bar there. The A median is somewhere there. The A median is there, the B median is there. They're separated, so B's bigger. If they were overlapping, then I couldn't tell. Right? Now this thing signals from sampling variation very, very seldom, about 1 time in 40. So sampling variation will almost never produce things this big. And all that's on the tech notes on page 5. There's one little thing I will, this is for the smarter kids, but you can read a little confidence interval for the true difference of here. You just take the smallest distance you can see, that's how small the difference could be. You take the biggest difference you can see, that's how big the difference could be, and there's your confidence interval. Okay? And you don't even have to make it into numbers. You can get a quick visual impression of how much uncertainty there is there about the difference. Anyway, okay, here's a quick summary. Where we've been for this talk, sampling variation alone can produce shifts in our box plots. We get small shifts with big samples, big shifts with small samples. It makes no sense to read meaning into shifts in data of a size often produced by sampling variation. That's just obvious. We've got some rules for signalling when a shift has occurred, when we can say that we believe there's a real shift. And that's when the shift is big enough, what am I saying here? It's big enough that we can make a call on what group gives bigger values. Okay, that's what the rules are about. So the question is, does the shift we see look bigger than sampling variation would produce? Here are our rules. They take sample size into account, because it's very, very important. They can be operated almost entirely without taking the eyes off the data, so you're still keeping in your mind what this is all about. They get more sophisticated as you go through from sort of 5th form, 6th form, 7th form, and they're converging towards the tools of formal inference. We're getting very, very close to proper confidence intervals by level 6 there. There's everything on one page. Curriculum level 5, the 3/4 half rule, is the median for one outside the box for the other. The majority of one is to the right of the great whack of the other. Not sample size dependent. Step it up a level when they come back at level 6, and then we're starting to look at the distance between centres. We're comparing it to some measure of spread, which is how much variation, how much spread we can see in the boxes, and then we're comparing that to a 1/3 or a 1/5, depending on sample size. Step it up to the 6th form, we put on these little constructed intervals, simple little formula, and we look for overlap. Okay. Now, the big question to you, I suppose, is, and we haven't got time to answer it, to get you to answer it, is does that look simple enough for kids to be able to do? If it does, then our months of work haven't been wasted. Okay, if the shift isn't big enough, then we can't make a call on who's bigger back in the populations. We simply don't have enough information. And that sort of thing happens frequently, either when the sample sizes are small, which means we have very little data, or a very ripply window, lots of distortions. It also happens when the differences between the populations are small. And what's going on there? We're looking for fine details, fine rather than gross discrepancies. You can't see them through ripply grass. But that's all subjects for other talks, I guess. And that's back to my sort of image that I've based all of this on. Looking at the world through, using data is like looking through a window with ripples in the glass. The ayes have it. And thanks.